Good afternoon, everyone. It's a pleasure to be here with all of you. My name is Brad Mortensen. I'm the president at Utah State University, and I'm honored to be able to spend some time with you today. Events like Research Landscapes are an opportunity to highlight what makes Utah State such an important part of our state. As the state's only land-grant university, we have a responsibility to put knowledge to work for the people that we serve. That means producing research that's useful, accessible, and grounded in the needs of our communities. Whether it's land, water, or air, our natural resources are central to our quality of life. They're also a part of our shared responsibility. So I want to thank each of you for taking the time to come today and to be part of this discussion, and hopefully that we can make a better future for Utah through events like this. As Utah continues to grow, we're navigating complex questions about how to balance growth with sustainability. Dr. Kopp's work helps us understand not just the costs of our landscapes, but the benefits: cooler cities, cleaner air and water, and healthier communities. As an R1 research university, we are committed to tackling Utah's most pressing challenges and contributing solutions that make a difference. And as someone who graduated from USU myself, this work is personally meaningful. I'm grateful for the opportunity to serve a university that shapes so many lives, including my own. I'm proud to be a part of a university that's also asking the right questions and helping build a stronger future for our children, our grandchildren, and the generations that follow. Thank you again for being here, and I hope you enjoy today's presentation.
Thank you, President Mortensen, for your remarks, and thank you for taking time to be here with us today. I know you have a very busy schedule on day 4. That's right. Okay. I'd like to take a few minutes to tell you a little bit more about our speaker, Dr. Kelly Kopp. Dr. Kopp is a professor and extension specialist in the Department of Plants, Soils, and Climate at Utah State University. Her research interests are focused on landscape water conservation, irrigation technologies, and sustainable turfgrass management. Kelly has worked at Utah State for more than 20 years, and during her time at the university, she has made valuable contributions to her research area and to the community. As an extension specialist, she shares her research findings with clientele groups and citizens throughout the state and region. She also directs USU's Center for Water Efficient Landscaping, holds a board position with the Professional Grounds Management Society of America, and is a U.S. representative to the International Turfgrass Society. As you might imagine, with those affiliations, Kelly works very closely with many federal, state, and local agencies and organizations to improve water use efficiency in the state of Utah, something we all know is incredibly important. She also helps to serve the Intermountain West and beyond. Please join me in welcoming Dr. Kelly Kopp.
Thank you. Thank you, Dr. Burrow. And thank you, President Mortensen. It was really a nice surprise to learn that you would be here today. And thank you all. I'm really touched by the faces I see here today, people I know who are friends, professional colleagues who are friends. Those of you who I don't know, I also very much appreciate you being here. And I'll begin in just a moment, but I'd like to start by sharing how I decided to embark on the work that I'm going to share with you here today. I've been at USU for actually 25 years now, and for all of those years I have been in the Plants, Soils, and Climate department. And while I do have a background in plants, soils, and hydrology, I have had nothing to do with climate over my career. And after 22 and a half-ish years, I would say, in the department, I decided that after lots of conversations with climate scientists in the hallway, meetings, etc., I started wondering how I might incorporate climate into my research, and more specifically, climate resilience. And that led to the work that I will be presenting today. But just before I begin, as Dr. Burrow mentioned, I do direct USU's Center for Water Efficient Landscaping, and I'd like to share a bit with you about the center and its mission. We are a group of 5 faculty members, 2 research technicians, and anywhere from 6 to 12 graduate students, depending on where we are in terms of funding and project support. We conduct research, education, and outreach programs, and our mission is to support Utah's landscapes and continue to enjoy the quality of life that we appreciate from them. So, having said that, on to green spaces for the 21st century. So I define green spaces as ornamental landscapes that are purposefully designed to integrate aesthetic, ecological, and social functions within the built environment. And that's in contrast to purely vegetated landscapes that may be used for agricultural purposes or utility purposes, because these landscapes emphasize beauty, they emphasize design and experiential value, while also delivering ecosystem services. So these are places like your residential yard, your public parks, your institutions, your university campus grounds, corporate grounds, botanical gardens, can also include things like golf courses, cemeteries, and streetscapes, just to name a few. Often when we think of infrastructure, we do think of buildings, or maybe we think of highways or other transportation systems, but infrastructure can also be green. And typically when we're thinking of green infrastructure, we're thinking of how it might affect stormwater management, because green infrastructure actually uses filtration, infiltration, and evapotranspiration to treat and soak up rainwater. And so the plants and soils and other media in our landscapes actually work together to filter pollutants, to promote infiltration, and to return water to the atmosphere through evapotranspiration. And green infrastructure can be implemented in lots of different scales. It can be at the regional scale, it can be at the neighborhood scale, and it can even be at the single site scale. So some of the benefits that we get from green infrastructure are social benefits and economic benefits, as well as environmental benefits. And I am certainly not a sociologist, nor am I an economist, so I'm not going to focus on those areas, except to note that improved health and well-being, a greater sense of community, more industry-related jobs, reduced wastewater management costs, and reduced flood damage costs are some of the benefits that we realize from green infrastructure. Now, sadly, we do have very recent examples of what can happen when stormwater systems are challenged. Just last month, on October 6th, Salt Lake City Mayor Mendenhall declared a local emergency following severe storms that flooded the Rose Park area. The previous weekend, approximately 2.5 inches of rain fell in just 14 hours. And according to National Weather Service reports, this was the most rainfall ever recorded in a single day in Salt Lake City over the more than 124 years of record keeping. The focus of this presentation, though, are the environmental benefits that we gain from green infrastructure. As green infrastructure, our green spaces not only reduce localized flooding, but they also improve water and air quality, they reduce heat island effects, they improve habitat connectivity, and they improve climate resilience by helping us address the challenges of heat, drought, extreme weather situations, as well as wildfire. But which green spaces are actually the best, and why are they the best, and how then do we choose? The project that I'm presenting today takes a life cycle assessment approach to help identify the landscape designs, the plant materials, and the management practices that provide the most benefit to us. Of course, we do focus on water efficiency in this work, but there are also other benefits to be realized. What are they? We are going to find out. Which green spaces are the best? Why are they the best? And how do we choose? As I mentioned, we do have in this project 5 landscape approaches with 4 replications each, and that includes 20 experimental plots in total. In 2022, we began by installing the irrigation systems and controllers in the plots. We started installing the plant materials in 2023 and completed that in 2024. We employ all of the best management practices as we know them to date to manage these landscapes. And we have begun collecting data and will continue to do so for the next 10 years, and I will explain that time frame as I'm going along. Okay, as I mentioned, we do have 5 landscape designs, and these include turfgrass landscapes with both standard water use and low water use turfgrasses, high water use localscapes, and I'm going to explain more about localscapes in the next slide, low water use localscapes, and strictly ornamental plant landscape, as well as a thyme lawn landscape. So for those of you who may not be familiar with localscapes, localscapes is a program and a design approach that was developed at the Jordan Valley Water Conservancy District many years ago. It includes 5 concepts, including central open shapes, gathering areas, activity zones, paths, and planting beds. And when I was developing this project, I had a few conversations with friends and colleagues at Jordan Valley who asked that I include localscapes in this research. And since it is a statewide program, it made very good sense to do so, and so I have included it here. To give you a sense of how the project developed, I'll go through a brief progression here. As I mentioned, the project began in 2022 with the transition of one research area from one project to this one. The previous grass areas were removed and the trees for this project were planted. We then began the process of installing new grasses in the landscapes in their designated positions, as well as other ornamental plants in 2023. On the right, you can see one of the ornamental plant landscapes just after we planted it. And here you can see on the left the thyme lawn landscape and everything fully planted on the right when the landscapes were just brand new. We began data collection on the landscapes in 2024, and that includes weather data, water volume, what we were applying to the landscapes, soil moisture, soil health and quality, plant morphology, plant physiology characteristics, things like stomatoconductance, soil gas flux, carbon sequestration in both soil and plant tissue, as well as what is evolving from the soil, and thermal imagery. The reason that we are collecting thermal imagery data on the plots has to do with increasing concerns about urban heat. We know, for example, that summers have been getting warmer since 1970, and that is especially true in our cities. Related, the Climate Central Group at Princeton University regularly evaluates increases in urban heat across the country at 10-year intervals. From 2003 to 2013, the cities that experienced the most urban heat increases were Las Vegas, Albuquerque, Denver, and Portland, with increases ranging from 7.3 to 4.8 degrees. From 2014 to 2024, the cities that increased heat the most were New York City, San Francisco, Newark, and Chicago, and those increases ranged from 8.7 to 9.7 degrees. But we know that our green spaces provide atmospheric cooling and can potentially help to address these urban heat issues. In fact, research conducted here in Salt Lake City found that turfgrass evapotranspiration and tree shading significantly shape microclimates of semi-arid cities like Salt Lake. Parks mitigate urban heat island effects here, especially when they include irrigated turfgrass areas. And combining dispersed trees and irrigated turfgrass areas maximizes both daytime shade and nighttime cooling while balancing water conservation. So how are we collecting our thermal imagery?
Final checks. That. Those are clear. All right, arm the aircraft.
We fly a very small plot in Logan, and we use a Megasense camera called an Altum PT, which provides us with 7 spectral bands that enable us to look at different aspects of vegetation. So we can assess the health of vegetation. We can look at the thermal characteristics of vegetation, whether they're perhaps receiving enough water, are areas overwatered. Really can vary from flying rivers, looking at fish habitat, flying cities, looking at sort of structures. I mean, it's just so broad. Back in 2006, the aim was to really concentrate on how we could enhance the sort of research in water-related issues. Kelly's come to us and asked for specific requirements, and I've said, yes, we can do it. We had a discussion about the imagery we could provide, and it went from there, basically.
And so, we are collecting thermal imagery of our landscapes to quantify the associated atmospheric cooling. Aggie Air, who you just heard from, takes these images for us 3 times per year. And you can see thermal imagery from 2024 across the top of the slide and 2025 across the bottom. The darker green colors indicate cooler temperatures, and the yellow, orange, and red colors indicate warmer areas. The resolution in this imagery is 7 millimeters, both horizontally and vertically. And that's going to allow us to develop temperature profiles for each of these experimental landscapes. So to assess our landscapes and to begin to quantify their environmental benefits or ecosystem services, we're using a life cycle assessment approach. Generally speaking, life cycle assessments measure the environmental impact of all the factors involved. They look at the cost and the type of materials used, how each resource interacts with the others as well as the world around it, and every detail is tracked. We consider the gasoline it took to get the plants we purchased from the nursery to our research farm. We consider the cost of that plant material, the pesticides and fertilizer used, among many, many other things and pieces of information that we collect. Now, this is often an approach used by companies who are looking to improve their environmental footprint, decrease their environmental impact, but we have adapted the concept for our purposes and created what we call the value landscape engineering model. We originally developed this model in 2011 in collaboration with a colleague in engineering, Dr. David Rosenberg, and other members of our Center for Water Efficient Landscape. And it allows us to compare our landscapes in terms of cost, water use, energy consumption, fertilizer and pesticide use, labor, fuel, carbon sequestration, among other things. But we now have the field data to update and validate this model, which we did not have before. And that's what I'd like to begin sharing with you now. So the slides I'm about to show you, we're going to get a little bit data heavy, so forgive me for that. But we're considering the years 2024 and 2025 for which we have collected data and making a few assumptions that I'll share with you now. We have scaled up the information from our landscapes to reflect 9,000 square foot landscapes. We are using 2024 and 2025 evapotranspiration rates, 2024 and 2025 water, fuel, and power rates, 2024 and 2025 summer and winter household energy use averages, and also assuming that the labor provided is owner applied. So, in terms of cost, what are we seeing? The most expensive landscapes in 2024 were the ornamental plant landscape and the high water localscape, followed by the standard turfgrass landscape and low water localscape. The least expensive landscapes in 2024 were the low water turfgrass landscape and the thyme lawn. In 2025, things changed a bit. The most expensive landscape became the standard turfgrass landscape, followed by the high water localscape, the ornamental plant landscape, and the low water localscape. The least expensive landscapes were the low water turfgrass landscape and the thyme lawn. Moving on to water, in 2024, the most water was applied to the standard turfgrass landscape, followed by the high water localscape and the low water turfgrass landscape. These were then followed by the low water localscape, the thyme lawn, and the ornamental plant landscape. In 2025, the most water was still applied to the standard turfgrass landscape, followed by the high water localscape and the low water turfgrass landscape. The least water was required by the thyme lawn, followed by the ornamental plant landscape. Energy was a little simpler. The only piece of equipment we use to maintain these plots is a battery-powered lawnmower. And so the only landscapes that had any energy associated with them were the turfgrass landscapes, which were very similar for both years, and then the localscape landscapes, which also had small turfgrass areas. They were also very similar for both years that we have had so far. On to labor. In 2024, the most labor was required to maintain the ornamental plant landscape, followed by the thyme lawn and the localscapes landscapes. The two turfgrass landscapes required the least amount of labor. In 2025, things changed a bit, and the most labor was required by the low water localscape, followed closely by the ornamental plant landscape. These were followed by the high water localscape and the turfgrass landscapes. In this project, we are also developing hydrocarbon balances for the landscapes. And as you can see, the values are negative. And this is because we are balancing the carbon associated with maintaining the landscapes against the carbon that is sequestered in the landscapes in the soil and plant system. So in 2024, the ornamental plant landscape sequestered the most carbon, followed by the high water localscape and the low water localscape. The least carbon was sequestered by the standard turfgrass landscape, the thyme lawn, and the low water turfgrass landscape. In 2025, the ornamental plant landscape again sequestered the most carbon, followed by the localscapes, the standard turfgrass landscape, the low water turfgrass landscape, and the thyme lawn. Now with this model, we don't just consider each year that we're collecting data. We can also project to any time frame we might like. So if we want to, for example, consider the 30-year life cycle of these landscapes, we can do that. So with these same landscapes, considering a 30-year life cycle, we found that the ornamental plant landscape cost the most, followed by the thyme lawn, the localscapes landscapes, the standard turfgrass landscape, and the low water turfgrass landscape. In terms of water, over a 30-year life cycle, the standard turfgrass landscape required the most, followed by the low water turfgrass landscape, the high water localscape, the thyme lawn, the low water localscape, and the ornamental plant landscape. So hopefully you can see how we have to start balancing our choices. While the ornamental landscape might be the most expensive, it also uses the least water in the time frame that we're considering here. The energy required to maintain these landscapes over 30 years is very similar to what I showed you with the 2024 and 2025 data previously, with the turfgrass landscapes requiring the most energy because of the mowing, followed by the localscapes, which also required some mowing. The ornamental plant landscape and the thyme lawn did not require any power equipment for maintenance, required quite a bit of human power, but no power equipment for maintenance. Considering labor over the 30-year life cycle, the most labor is required for the thyme lawn landscape. I'm going to pause. Does anyone want to guess why that is? Yes. Weeds. Indeed. Those thyme lawns, the only thing you can do to remove weeds is hand pull weeds. So that is the reason that the thyme lawn landscape required the most labor, followed closely by the ornamental plant landscape. These were then followed by the low water localscape and the high water localscape. The turfgrass landscapes continue to require the least amount of labor. And finally, the hydrocarbon balance after a 30-year life cycle is similar to what we found in 2024 and 2025, with the ornamental plant landscape sequestering the most carbon, followed by the localscapes. The thyme lawn and turfgrass landscapes sequester the least carbon over that time frame. And this is an area of the work that we, of course, will be collecting field data for, but it's also an area of the work where I pay very close attention to what's happening in other places and other research that's being conducted, so that the numbers that we put into our model to help us calculate this are as accurate as they can possibly be. So not only with the hydrocarbon data, but with all of the data that we are collecting, we are also paying attention to research that is happening elsewhere to inform what we're doing, to help us be as accurate as we can possibly be. So part of this project is figuring out how to make this model useful and broadly available. And so we have done some beta testing with it out in the so-called real world and have had feedback like, you should provide a set of scenarios or default landscapes to demonstrate how this model works. You should consider some sort of score or landscape efficiency factor so that people could make a choice. You could include a summary page that would incorporate all of the savings aspects that you found by year, And lastly, folks thought if we could make this available online, perhaps through some sort of widget, it would be much more accessible and easy to use. And I agree with that wholeheartedly. So to sum things up, this is a very long-term project, primarily due to our interest in the carbon balance, which can take a very long time to develop. But this time frame will also allow us to consider how actual costs change over whatever time frame it is we want to consider. And we are currently able to model the first 2 years based on data we've collected in the field, but we will continue year over year to do that as the project goes on. This model can be adapted to local conditions and costs, which is what I've done today with the information from Salt Lake City, which does make it broadly applicable. And we hope that it will help homeowners, agencies, cities, utilities, and whoever manages landscapes to make well-informed choices based on life cycle considerations. And in the end, we really hope that by helping people make well-informed landscaping choices, they will understand that they have something to contribute to our resource challenges, even at the small scale of their own yard or landscape. And while individual contributions may be small, together they can add up to very big solutions. Thank you. And now we're going to have some Q&A, I believe. Yes.
Yeah, so before we get started, I just want to set the tone for this. When we bring research to you through Research Landscapes, it's meant to be a discussion. It's meant to be an opportunity for us to hear from you and for you to spur our thinking about how we should be moving forward in research. So I'm going to run around the room with a microphone. Please raise your hand and I will be happy to come to you, and we'll have a conversation for about 15 to 20 minutes. So, hey, we got the first hand up.
Thanks, Kelly, that was awesome. I was just kind of surprised to see that the least carbon sequestration was taking place in the turf areas, where I would think like turf grasses, fibrous root systems, we think of some of the most like carbon-rich soils are,
yes.
you know, kind of the tall turf grass prairie areas. I'm just curious what your theory is on why that was, and maybe in more time in turf that those soils might be.
Yes.
What are your thoughts on that?
Yeah, excellent question. I was a little surprised myself, but I can just share that the carbon sequestration aspects, we are directly measuring them, but for our model, we had to start somewhere, right? And so I had to look at the existing research and figure out what can we assume is going to be the carbon sequestration rate for turfgrass areas. And unfortunately, there's just not a ton of research out there specifically focused on turfgrass areas. But this is why we're doing this project for this length of time. I'm hoping to add to that body of research. And like I mentioned, we're always paying attention to what's going on. I'm aware now of some additional research on turfgrass carbon sequestration that I'm going to be incorporating. But yes, I agree. I was surprised by that. And for those of you who may not be familiar with this area of work, one might assume, based on the fibrous root structure and how turf grasses grow, grasses in general, that there would be more carbon sequestration there. I suspect things will change as the project goes on, and I'm certainly happy to share that with you as it does.
Ellen Burrell, I'm with the Kopp City Council.
I remember you.
Yes, and this sparked so many thoughts. I had my formative years in Southern California, and here in Utah, 44 years, you know, we have certain grasses, and I really appreciate USU taking a lead, and we're trying to get that information out throughout our city to our residents. And I just had a trip in California and was reminiscing about how my father grew dichondra. Does anybody remember dichondra? Oh my goodness, almost. Well, my dad planted our lawn in dichondra in 1958. And it was beautiful, and we played on it. It held up just fine. Anyways, I looked that up, and so I'm sitting here now and seeing thyme. And I don't know if thyme, like dichondra, has a broad leaf. But I wondered why dichondra just suddenly went away, let's say sometime in the 1960s, which I think has to do with the chemicals industry wanting everybody to have grasses where they didn't have to weed them. So comment about the well, I'm wondering two things. So how does our society help to dispel this idea that what grass you plant doesn't really matter because you're going to put a bunch of chemicals on it every year?
Oh.
And since I know everybody in this room shares my desire to see us put less of those chemicals, did I turn it off somehow? No, it died. It just died. But anyways, I just want to open up that subject. I'm wondering if you can make comments.
Part of the reason we embarked on this research was to show people that there are alternatives. And you know me, I talk a lot about different turfgrass alternatives, but turfgrasses aren't the only thing out there, of course. And I don't ever want anyone to think that I stand for having more turfgrass or even keeping as much as we do have. I do not. My main focus is to, one, conserve water that we apply to our landscapes, and two, do so in a way that doesn't land us with a lot of unintended negative consequences that we don't like very hot cities or really bad stormwater issues. Because the fact is, grasses do an incredible job of slowing down water and allowing it to infiltrate, as well as removing pollutants from that water. So it's a question, which is why we do work like this. We're trying to answer that question. Now, if I were designing this project again, I might consider other ground covers besides thyme, which has a very narrow leaf, by the way, to answer your question, but including things like dichondra. But dichondra, there's some issues growing that in our climate. So that's part of the reason that you don't see it here.
But you don't see it in Southern California either.
Well, that I really don't know about. But I do know, I mean, maybe there are some other folks in the audience that know better than I do, but I do know that there is a lot of focus on alternative ground covers in California. Perhaps not dichondra, but carapia, for example, is one that I've heard a lot about recently, and there are others.
Christopher, Salt Lake County. I was curious if there was a standard for how all these plots were watered as well.
Ah.
Irrigation systems could affect
Yes.
results.
Okay, so excellent question. I'm really glad you asked it because you're giving me the opportunity to explain how we irrigate these plots. So when I mentioned we use best management practices, we do. We use the best management practices we know of to this point, and that includes climate-based irrigation control on these plots. For those of you who may not be familiar with that, we have available to us now in the world of irrigation technology many, many options for irrigation controllers that take local weather data and allow or don't allow irrigation based on what's happening locally. So we are using that type of controller on these plots, and in addition to weather data, it considers your plant material. So we have programmed, okay, these landscapes have this much turf, it requires this amount of water. These other landscapes have these ornamental plants, it requires that amount of water. Very detailed programming so that the irrigation applied to each type of plot is appropriate for that plot and based on local weather conditions. So they're all getting different amounts of irrigation, the different types of landscapes. Does that answer your question?
Yeah, I guess they're also, are they like typical sprinkler heads?
Oh, okay.
What was utilized, I guess?
Okay, also a great question. Sorry, I went totally down the wrong path there. So these plots, in addition to using the best irrigation controllers we can use, we also use the best irrigation components. So the ornamental areas, the tree areas, that's all being irrigated with drip irrigation. The lawn areas and the thyme areas are irrigated with a type of sprinkler called a multi-stream, multi-trajectory sprinkler. This is, if I may do a demonstration, this is a type of sprinkler that puts water out in a pattern like this. And they are so much more efficient than a standard spray head. It's a little bit shocking, frankly. So again, we are using the best products, the best technologies that we have available to us. You're welcome.
USU forestry grad, so I'm looking at the trees and seeing some young trees here. Do you have mature trees? Are you looking at different types of trees and their cover and their different water characteristics and usage?
So they're brand new landscapes. We thought we'd start at square one, but all of the landscapes have a single tree on the southwest corner. because that is where you might plant a tree if you were trying to provide cooling or protection from wind, etc. They are all the same type of tree, I'm sorry to tell you that, very young. They're all linden trees, and we picked these trees because they were available, widely available. I actually talked with a colleague of mine, Dr. Larry Rupp, who's since retired. He's the one that helped me decide on the trees. And lower maintenance, relatively quickly growing, but they are all, I do admit, very young, yes. As is every plant in these landscapes. Yeah.
Nathan Hole, actually, with Posey County. My main question, kind of when I was looking at this, I think in the field there's a lot of discussion around, do we do xeriscaping, do we do grasses, and one of the biggest questions for that is because of the heat island effect, especially in cities. So I guess how would you recommend balancing that, those benefits of that water conservation versus that heat island effect?
That is the question we are trying to answer. I will tell you that when I was starting out thinking about this project, of course I'm always thinking about water, always. But I've also become aware of some issues that come from removing turf grass. There are many, we could discuss that at length if you like. But we did this project so that we could try to answer that question. But if you also want to think about it on a more individual scale, maybe wherever you are in your particular situation, you're more concerned about sequestering carbon, or maybe you're more concerned about that urban heat effect, or maybe your primary concern is water. When I talk about this project, I often say that maybe you have to spend a little water to realize some of the other benefits, right? But how much of that is appropriate? And in the beta testing, that's what people wanted. They wanted a score. They wanted an efficiency measure, something that they could say, oh, okay, that's the winner, and that they maybe didn't have to think about so much. But unfortunately, it is really complex and is very situation specific. So I hope to be able to better answer that question as time goes on, but it is very complex for sure.
Good afternoon, Soren Simonson of the Jordan River Commission and Watershed Council. The question that I have, it looks like this is just a couple of years in a long-term kind of research project, maybe 10 years or so, it sounds like. Will data be available on an annual basis? Where would we find information about this to kind of watch and observe what's happening?
Yes, data is definitely going to be available on an annual basis, and my plan is to have that available on our Center for Water Efficient Landscaping website and to keep that updated as we collect the data. I will also be publishing papers, peer-reviewed research papers from this work, but that's maybe not so publicly accessible. So I think the best bet is going to be looking at our website over time. And also, by the way, that's my email address. I'm very happy to stay in touch with you about it. Hi.
With Division Water Resources. I just had a question about the hydrocarbon sequestered. Is that offset with the power equipment usage that you were showing, or?
Yes.
Okay.
Yes. So that's the idea. We're balancing that power equipment usage against what's sequestered, which is why it ends up being negative. If we were using gas-powered mowers, that would be a different graph, right? But again, we're trying to use best management practices, the most environmentally responsible practices we can, so we're using battery-powered equipment, which in our case just means a lawnmower right now. It may come to be that we need power equipment for handling some of the shrubs or trimming and things like that, but as of yet, we haven't needed that.
I was wondering about the ornamentals.
Uh-huh.
So the carbon sequestration looked really good.
Yes.
And so I was wondering if you have any guidelines for selecting ornamentals. Would you expect to get a different profile as you make different choices?
So the way that we have built the model, it's based on data that exists so far, that because we didn't have any data when we began the project. So we looked at existing research for that. And that they're pretty general. For example, there is sage in that landscape, but there isn't necessarily research out there to tell you this size of a sage plant is going to sequester this amount of carbon. It's more general than that. It's more like small, medium, large shrub or It might have something to do with low or high water use shrubs. So we have sort of general information there. But now we are collecting the actual data. We're collecting plant tissue, we're collecting soil samples, and we can quantify that. So we will have that information for our plots for the plants that we are actually growing there. This, though, at this point is based more on existing research and more general information that's available to us.
My question is regarding soils.
Yes.
I'm assuming with all this being on the same plot that all of these have the same soil type.
That's correct.
So like we're not seeing a difference in how a higher sand content of soil would vary from a higher clay in affecting those landscapes. But are you also testing for each of these landscapes how the soil health changes?
Yes, great question. So in addition to urban heat, soil health is something that is such a hot topic right now, and we are absolutely looking at that. But you're absolutely correct, they are all installed in the same soil, and it is a beautiful, beautiful silt loam soil in Cache Valley. But soil health is critically important, and we can monitor microbial activity, we can monitor, that list of data that I showed you is really partial. We are collecting so much data and there is so much instrumentation on these plots, it's a little bit overwhelming at times. But we are absolutely considering soil health because soils, I'm on a soapbox here, soils are like the key to the kingdom, right? If we don't have good soils to support our plant materials, which then support us, we're in trouble. So we need to keep it in place, we need to prevent it from eroding, and we need to maintain its quality. So that is definitely something that we're looking at over time. Yes?
Hi, my name is Dan Sontag, I work for Salt Lake County. My question is about how you went about selecting the plant material, and what's the difference between localscape high, localscape low,
Yeah.
ornamental?
Yeah.
Which turf types did you select?
So, okay, the difference between localscapes high and low, and I'm happy to be able to explain that for my localscape friends. With the localscape high, it's higher water use plant materials. So it's standard water use turfgrass, it's higher water use ornamentals that are very commonly used in Utah. Low localscapes, low water use, it's the opposite. So there's low water use turfgrass there, as well as low water use perennial shrubs, etc. The ornamentals, a lot of the choice had to do with, now keep in mind, we're doing life cycle analysis, right? And so some of the plant choice consideration was, where are we going to get it? How far is it going to travel? And how much does it cost? And is it available? So some of the decisions were frankly made because it was what was available to us close by. We were trying to be very intentional with that. If we can reduce the amount of transportation, that has a bearing on fuel and other things as well. So that was some of the consideration with the decisions we made on plant material. You also asked about the turfgrass. So the standard water use turfgrass was something that we got from a local sod farm to our area in Cache Valley. And that same sod farm actually now grows low water use turfgrass, which has a water requirement about 40% less than standard water use grasses. So those were the best materials available to us for those demonstration purposes. Does that help?
That sod type, the one that was the winner from your previous experiment with all the grass?
Oh, when we trial things? Is that what you mean? It's actually a blend. So it's a blend of Kentucky bluegrass and tall fescue and multiple varieties of each. That's true for both the standard turfgrass and the low water turfgrass, which is an approach we generally recommend, not a single species or variety, but a mixture and a blend. Yeah. Well, but if I can answer just a little bit more on that, it is kind of the result of some of the previous work we've done testing turfgrasses. Because at USU, we do a lot of turfgrass trialing. We participate in just about every trialing program in the country. But the one I'm most interested in is the ones that we do for the Turfgrass Water Conservation Alliance. And the whole goal of that program is to identify grasses that are very low water use. So from some of that work we've done, these species were developed, yes.
I'm curious about what kind of outreach you're doing to try and get this in front of people, obviously this, but like,
Yeah.
are you inviting people to your research
Yeah.
location?
Yeah.
And what does that kind of look like? What kinds of people are you trying to attract, and what are you talking about when you're on site with them?
Yes, we're absolutely trying to get this out there. We have field days at our research farm about every other, well, this past year I think we had 2 different field days. So we do invite various groups to come and have a look. I'm also very willing to give anybody a look who wants to come and have a look, frankly. And I have had a lot of opportunities actually to present this information, not just here, and I'm going to be presenting it this January, both at the Utah Nursery and Landscape Association Conference as well as the Idaho Nursery and Landscape Association Conference. And, by the way, this work was funded in part by the Scotts Miracle-Gro Foundation through an organization called the Alliance for Water Efficiency. That's an organization, it wasn't in my bio because I'm not on the board anymore, but for many years I was on the board of that organization, and that is a national organization. They are cooperating with me on this project to get this out to folks in the nation. So we're doing this work here in Utah, but it has much broader implications.